Okay, and now we are ready to state our main theorem with all these things in place. So let me state the following characterization of Galois extensions. Let K over F be an algebraic extension then the following statements are equivalent. Okay, the following are equivalent. The one, that K over F is a Galois extension property 2, if gamma denotes the group aut K over F, okay, F automorphisms of K, then the fixed field of gamma is exactly F. Okay, and property 3, statement 3 says for all elements alpha in K, its minimal, for each alpha in K, its minimal polynomial m alpha of x. So its minimally reducible polynomial over the base field F splits into a product of linear factors. More than that, the linear factors are distinct. Okay, so it splits completely, but it doesn't have repeated roots, okay, in K. And this is really the characterization that we now want to prove. Now observe that in some sense 1 and 3 are really, the same thing. We have, we talk about normality and separability, and observe that to say that the minimal polynomial of every alpha in K splits completely was one of our equivalent characterizations of a normal extension. And the other fact that the minimal polynomial is separable, meaning it has no repeated roots, was exactly the characterization of separable extensions. Okay, so quick observation here is that 1 and 3 are really equivalent to each other. Okay, so let's prove this. Start with the observation that 1 and 3 are really the same thing. And why is that? Because normality, according to what we proved in our lecture on normal extensions, is the following, that every minimal polynomial, every m alpha of x splits in K, okay, into linear factors. But at the moment they could be repeated as well, but separability ensures distinctness of those linear factors. So separable says that every m alpha of x has, so I should say m alpha of x has no repeated roots. And this is true for all alpha and K. Okay, so looking back on what we have already proved, normal and separable is exactly what statement 3 encodes. Okay, so that's done. What we are really looking for is this new property 2, the new characterization, which says that if you take the set of all F automorphisms, then the fixed field of that group is exactly the base field. Okay, so let's prove that 2 is equivalent to 1 and 3. So I'll prove it as follows. Let me show first that 1 implies 2. So if it's a Galois extension, then the fixed field of the group of F automorphisms is exactly the base field. So first observe, the base field is certainly contained inside the fixed field. Okay, so now I'm just using the notation of the theorem. Gamma is going to denote the set of all automorphisms of K over F. Then we need to show K gamma is F, but one way is clear, F is always a subset of K gamma. Okay, why is this? Because what is K gamma? It's a set of all elements of K which are fixed by every element of gamma. Okay, but gamma is the set of all F automorphisms of K. Okay, and what's an F automorphism? It was an automorphism which is assumed to fix the base field pointwise. So it's all those automorphisms such that when you restrict it to elements, so sigma A is definitely A for all A in F. This is what restricting to F gives you identity means, exactly this. Okay, so it's clear that every element of the base field is going to be fixed by every element of gamma. Okay, so this property is clear. Now what we need to really prove is that the other inclusion also holds, which is that K gamma is contained in F. Okay, so we now need to show K gamma is also contained in F, and we will prove this by contradiction. So suppose not. Well, what does that imply? It says that there is an element, suppose not, or maybe we should, well, okay. So maybe we'll prove it as follows. Let's pick an element of, okay, so maybe let me not just say contradiction here. So let me say I need to prove this K gamma is contained in F. So I will pick an element that's not in F and show that it's not in K gamma. So contrapositive is really what I mean, I suppose, here. Okay, so we'll prove this as follows, i.e. if alpha is not in F, then alpha cannot be in K gamma. That's what we'll do. Okay, so let's do that. So let's pick an alpha. So let alpha be an element of K which is not in F. Okay, so K which is not in F. So K is an extension of F. I'm picking something which is not in the base field, and I need to show that it's not going to be fixed by every element of gamma. Okay, so what do we need to show? We'll prove the following. We'll show that there exists at least one element of gamma, at least one automorphism, such that we will show that there exists an automorphism which maps alpha to something other than alpha. Okay, if we show this, then we are done. Okay, if we do this, we are done. Okay, we would have proved what we want to prove, because this will tell you that alpha cannot be in the fixed field. Okay, at least one automorphism does not fix alpha. So this is all we need to prove. Okay, so how should we try and construct such an automorphism? So observe that alpha is in K but not in F means the following. Consider its minimal irreducible polynomial m alpha of x. Okay, same notation as in the theorem. M alpha of x is the minimally irreducible polynomial of alpha over the base field. This polynomial has degree at least 2. Okay, degree of m alpha is at least 2. Okay, why? Because the degree 1 polynomials are exactly the, if m alpha had degree 1, then it will tell you that alpha is actually in the base field. Okay, because the polynomial would be of the form some linear polynomial, right? It will look like x minus some constant. Okay, which means that alpha minus that constant is 0, so alpha itself is that constant. In other words, alpha is in the base field. Okay, because if degree m alpha is 1, then it just means that alpha is in the base field. Okay, in fact, it's an if and only if statement. Okay, now degree is at least 2 means the following. Well, what are we assuming? We are assuming 1, right? So we are assuming that the extension is normal and separable. Okay, so now here is an irreducible polynomial m alpha of x. Look at its roots. So look at K over F. I have assumed that it is Galois. So in other words, I know that this is a normal separable extension. Okay, which implies, or you can think in terms of property 3, which is the same thing. It says that this polynomial m alpha of x firstly splits completely, becomes a product of x minus alpha i's. I goes from 1 to d, where d is the degree of this polynomial. So d is the degree of m alpha. Okay, where the alpha i's are distinct numbers. That's the important thing here, right? The separability where alpha i's are in k and alpha I not equal to alpha j for I not equal to j. Okay, in other words, you have a split into a product of distinct factors. Now, so of course alpha is one of the roots here, right? So m alpha of x, of course alpha is the root of this polynomial. Let me assume the first root, alpha 1 is alpha. Say alpha 1 is your alpha. Okay. Now let's look at the second root. So recall there's at least one more root because the degree is at least 2. Okay, so let's call the second root as beta. So let beta denote alpha 2. Let beta be alpha 2. We know that, what do we know? We know beta is not the same as alpha, certainly. Okay. Now we'll construct our automorphism as follows. There exists an automorphism, there exists sigma in gamma. Gamma is, there is an F automorphism of K such that sigma maps alpha to beta. Okay, that's our claim. Now once you prove this, you're done because beta is not the same as alpha. Okay, now let's prove this claim. Again, it's an argument which we have seen before when we talked about normal extensions and so on. So for this, let's just bring in the algebraic closure. So it's convenient to have the algebraic closure here. So let L be an algebraic closure of the field K. Okay. So what I'm doing here is looking at K, there's the base field F, and now I'm putting L inside its algebraic closure. So observe again, algebraic closures, as you have seen before, are unique. Okay. In a certain sense, there exists, given any two algebraic closures, there is always a automorphism between them which restricts to an identity on the base field. Okay. Now, so what do we know? Well, let's do the following. We are trying to do this, right? We are trying to construct a map which takes alpha to beta. So let's do the following. For the moment, let's forget about K here. Okay. So I have L, I have F, and in between them, I am going to look at the intermediate field F adjoint alpha. Okay. This is a subfield of K, right? So recall that alpha and beta are elements of K here. So instead of looking at all of K, I will look at a certain subfield which is F of alpha. Okay, now let's do the same thing on the other side with beta in place of alpha. I look at F beta and I look at L. Okay, so I look at these two extensions. Now recall the following facts. Again, the same argument which we have seen before. So recall F alpha and F beta are actually isomorphic fields. Okay, there exists an isomorphism of fields. Isomorphism, we call it psi, from F alpha to F beta, such that with the following properties, psi restricted to F is just the identity map on F, and psi takes alpha to beta. Okay, so you've seen this before, and why does there exist a map like this? Well, abstractly, because both F alpha and F beta, you can think of both of them as being given by, well, it's a symbolic adjunction. So you think of F adjoint X modulo the minimal polynomial. Okay, and now both alpha and beta have the same minimal polynomial, which is m alpha of X. Okay, so F alpha is this, but then, well, that's really the same as the minimal polynomial of alpha and beta are the same polynomial F alpha of X. So you should think of this as also m beta of X. That's like F beta. Okay, so this map, if you just unravel this chain of maps, what it gives you is a map from F to F, a map from F alpha to F beta, which is identity on F, and which takes alpha to beta. Okay, so I'm just recalling things you have seen before. So at least we have constructed sort of a map which has the property we want, which takes alpha to beta. But now recall a second fact. So we need to recall a second fact here, which is when you have maps, so observe that L is also the algebraic closure of F alpha. Okay, it was the algebraic closure of K, but it's actually also the algebraic closure of F alpha. Okay, why is that? Because it's algebraic over, what's an algebraic closure? It's an algebraically closed field, which is algebraic, which is an algebraic extension of the field you are looking for. Okay, so here this is an algebraic extension and L is algebraically closed. This is what an algebraic closure is. Okay, and why is L over F alpha algebraic? Well, L is in fact algebraic over the base field F itself, right? So recall the original thing I had, L, K, F. K over F I had assumed to begin with was algebraic. L over K, well, L is an algebraic closure of K. So in particular, L over K is an algebraic extension. L, remember, is algebraically closed. Now, a tower of algebraic extensions, algebraic over algebraic, gives me something that's algebraic. So this overall extension here is algebraic. Okay, so it's in fact an algebraic extension of F. So in particular, it's an algebraic extension of F alpha. Okay, so it involves sort of putting together many of these ideas that keep recurring in this business. So now again, F beta, for the same reason, L is an algebraic extension of the base field F. So in particular, it's an algebraic extension of the field F alpha. And L is an algebraically closed field on its own. So L is therefore the algebraic closure of F beta. Okay, so what is the summary of this argument? It says that L is the, or if you wish, an algebraic closure of both F alpha and F beta. And now the fact to recall is that if I have two fields which are isomorphic to each other, so there exists an isomorphism between them, then there is a way to lift this isomorphism to an isomorphism of their algebraic closures. Okay, so if the base fields are isomorphic, their algebraic closures are also isomorphic. But a little more than that, if you have a certain, given any isomorphism psi between the base fields, it extends or lifts to an isomorphism between their algebraic closures. Okay, so this is again something you've seen before. So recall the following fact: there exists an isomorphism of fields psi tilde from L to L such that when you restrict psi tilde to the field F alpha, what you get is the original isomorphism psi. Okay, good. So where does this leave us? We are almost where we want to be. So now it's time to put the field K back into the picture. So we had the following. So I have a map from L to L, which is psi tilde. Okay, this map has the following property: when I restrict it to F, it just gives me back, well, in fact, if I restrict it to F alpha, so let's also put F alpha, it gives me psi. And psi, remember, when you restricted it to F, gave you identity. Okay, so we have this. Okay. And now, of course, between F alpha and L, you've got K. Similarly, between F beta and L, you have K. Okay, so this contains both F alpha and F beta. And now, recall that K is normal. Okay, so far we haven't used the normality of K. So K over F is a normal extension. Okay, so we have only used so far the fact that it's separable, because we said M alpha has, it must have distinct roots. So if alpha is one of its roots, then there must be a different root beta. Okay, that's all we have used so far. Normality hasn't been used yet, and now it comes into play. So what do we know? If you recall what a normal extension, one of the equivalent properties of a normal extension was, we proved that if K over F is normal, then any automorphism of the algebraic closure of K, any map psi tilde, which restricts to identity on F, must send K to K. Okay, so recall from our lecture on normal extensions. This means, recall that K over F is normal means the isomorphism psi tilde must satisfy the following property, that it must map K back to itself. It cannot send elements of K to elements which are not in K. Okay, so psi tilde maps psi tilde of K is exactly K. Okay, and this is to prove this, you need to know that psi tilde restricted to F is the identity. That's what makes this work, right? If you go back and look at the theorem for normal extensions. So the K over F is normal means that any F automorphism of L must in fact preserve K. Okay, so in other words, when you restrict psi tilde to K, what you get is in fact a map which sends K to itself. Okay, so let's call this map as sigma. So let sigma denote the restriction of psi tilde to K. Okay, now what is this? Sigma therefore is a map, it's an automorphism of K which is identity on F. Okay, so it's an element of aut K over F. Okay. Further, what property does sigma have? Well, sigma, when you restrict it to F alpha, is the same as the original map psi. Right? So sigma, when you restrict it to F alpha, was the map psi. This means that in particular sigma must map alpha to beta. Okay, and that concludes the proof, because that's exactly what we were trying to construct, an automorphism of K, an F automorphism of K which sends alpha to beta. Okay, and notice that we have used many of the properties that we have studied until now. So we sort of passed to the algebraic closure, use this general theorem which says you can always lift maps you lift isomorphism of base fields to isomorphisms of their algebraic closures, and then you sort of descend to K again by using the normality. Okay, F isomorphisms of the algebraic closures must preserve the normal extensions. They must map K back to itself. Okay, so slightly long-winded proof, but sort of a beautiful application of all the various ideas we have seen so far. So let's see where we are. So what is it that we needed to do? We needed to prove, so we said already that 1 and 3 are the same. So we have now shown that 1 is the same, well 1 implies 2. We've said 1 and 3 are the same. So we just need to show that 2 implies 1, okay, or which is the same thing, 2 implies 3. Okay, that's all we need to show. So let's prove that. So let's try and show that 2 implies 3. Okay, so that's the last part of the proof. So what do we need to do? We are going to assume that the fixed field of gamma is exactly F, and using that we are going to show that every m alpha of X splits into a product of distinct linear factors. Okay, so let alpha be an element of K and consider its minimally reducible polynomial m alpha of X. Okay, so we need to show that this is going to be an element, it's going to be a product of distinct linear factors in K. Now, let's do the following. So observe, at the moment we know almost nothing about the extension, right? We have just assumed something strange about the fixed field of the automorphisms, that's all. We don't even know, for example, that m alpha of X has any other root other than alpha in the extension K, right? We don't know that it splits. We don't know that it's separable. If it splits, does it have distinct roots? We know nothing about m alpha really. Okay, so it may not even have any other roots other than alpha for all you know. So, but anyway, let's write those roots down. It has some number of roots, alpha 1, alpha 2, alpha r belonging to K, be the distinct roots . Okay, let these be the distinct roots of this polynomial m alpha of X in K. Okay, so observe R is at most the degree of m alpha. We don't know that it has, exactly the degree number of roots. It probably has fewer. Okay, also the first root, definitely it has one root, which is, alpha definitely. So let's again say that the first guy is alpha. Let's assume that alpha 1 is your alpha. Now the key observation, so how do we bring in the automorphisms? Observe the following fact, that if I take an automorphism sigma of k over f, then sigma permutes the alpha i's among themselves. Okay, when I say alpha I mean it permutes this set of roots alpha 1, alpha 2, alpha r among themselves. Okay, why is this? Again, something that you have seen before. If in general, when I have a polynomial, so recall this fact again. If I have a polynomial, coefficients in f, and let's say f of some beta is 0, so let beta be a root, some beta, so maybe I should write it as let beta be an element of k such that f beta is 0, then if I look at sigma beta, okay, which is, so what is sigma here? Sigma is an automorphism of k over f. So if I take any sigma, an automorphism, and look at sigma beta, then sigma beta is also a root of the same polynomial. Okay, and we proved this. All you have to do is just write the polynomial f out and apply sigma to it. Just look at f beta is 0, you apply sigma to the equation, the coefficients will not change because sigma fixes the field f, right? You have assumed sigma is an automorphism of k over f. So sigma fixes the coefficients, the beta powers will all become now sigma powers of sigma beta instead. Okay, and that will show that f of sigma beta is 0. In other words, if beta is a root of f, then sigma beta is also a root of f. Therefore, sigma must permute the roots of f. That's exactly the fact we are looking at here. Okay, so we know for sure that sigma must permute the alpha 1 through alpha r among themselves. Okay, so now let's do the following. Let's consider the polynomial in kx. Okay, it's now got coefficients in k defined by the following, defined by, let me call it g of x, is just the product of the x minus alpha i's. I goes from 1 to r. Okay, observe this is not necessarily the same as m alpha of x, because m alpha of x may not factor completely, right? It may have some higher degree reducible factors and so on. Gx is only the product of the distinct linear factors which occur inside m alpha of x. Okay, so it's a priori something sort of smaller than m alpha. Okay, so one thing we know for sure is, of course, that alpha is equal to alpha 1. So alpha is certainly a root of g. Okay, now here's the very surprising claim in some sense that, well, at the moment g only has coefficients in k, right? We can't say anything more than that because the alpha i's are only elements of k, but the claim is g actually has coefficients in f. Even though it doesn't look like it, it actually has coefficients in f. Okay, and to prove that, we are going to use our hypothesis that the fixed field of the set of automorphisms is exactly f. Okay, so let's prove this. So what are the coefficients of g? So let's expand g out and see what the coefficients look like. So gx now looks like x power r minus summation of all the alpha i's, alpha I, alpha j, x to the r minus 2, and so on. So this is overall I less than j. So recall, this is how one expands polynomial, and these coefficients here are exactly the various elementary symmetric functions, if you wish, right? So these fellows are all symmetric functions of the roots, symmetric polynomials, if you wish, or symmetric functions. they are symmetric polynomials in the alphas. Okay, in other words, when you permute the alphas, these things don't change, right? These coefficients don't change. And in fact, they are what are called the elementary symmetric functions, if you know what they are. Okay, but for us, the key word here is symmetric, that these coefficients do not change if you permute the alphas among themselves. Okay, now what does that mean? It says that if, for example, let's take the first coefficient summation alpha I here. If I apply any one of the sigmas, any automorphism sigma of belonging to K over F, then sigma only permutes the alphas among themselves. So this will give me the same answer for every alpha, so for every sigma in automorphisms of K over F. Similarly, if I take the second coefficient, so first coefficient has a minus in front, the second coefficient doesn't, so these are all twofold products, the alphas, just gives me back alpha I, alpha j. Why? Because the only possible action of sigma is to permute the alphas. It will map each alpha I to some other alpha j, right? But then this final combination remains the same. Okay, this is again true for all sigma in aught of K over F. So what does that imply? Well, and so on. So you can see this is true for all the coefficients. So that means that the coefficients, so the coefficients of G, therefore all belong to K gamma. Okay, remember gamma is the aught Kf. It belongs to the fixed field of the group of automorphisms, F automorphisms of K. But the assumption, the hypothesis we started out with is that the fixed field of K gamma is exactly F. It is the base field. Okay, so that proves what we wanted. So therefore, the coefficients of G are in fact in the base field. So why is that? Because, well, they are really symmetric functions of the roots, and automorphisms necessarily permute the roots. Okay, wonderful. Now, why is that useful? Because if you look at G here, so we have shown that G is a polynomial in Fx, and G is a polynomial on which alpha vanishes, right? So what does this mean? These two things imply that m alpha of x, remember m alpha is the minimal irreducible polynomial, it's the minimal degree polynomial in Fx which has alpha as a root. Now G is another candidate polynomial, it's another polynomial which has alpha as a root. Then this just means that m alpha of x must divide G of x, right? The minimal polynomial always divides any other polynomial of in Fx which has alpha as a root. Okay, great. Now why is that what we want? Well, let's just analyze this a little bit. So if you look at m alpha of x on the one hand and g of x on the other, g of x is just the product. So what is this? So let's write gx out. This is now x minus alpha 1, x minus alpha 2. So observe G is now a product of distinct linear factors, and m alpha of x divides such a product. Now, so let's write this m alpha of x as, say, a product of irreducibles f1 of x, f2 of x, fs of x, okay, where f1, f2, fs are polynomials in kx which are all irreducibles. So I have factorized m alpha into a product of irreducibles in kx, and this product of irreducibles divides this product of irreducibles. It divides the product of the linear factors. This means that each fi, so each irreducible, so look at any given fi, it divides the product of the x minus alpha j's. That means it must divide at least one of those factors, right? So each fi has to divide at least one of the x minus alpha j for some j. Okay, some j depending on I, of course. So each fi will potentially divide a different x minus alpha j depending on I. So what does this mean? Well, this means that if you write out m alpha of x, which is a product Well, fi is irreducible and x minus alpha j is also irreducible, a linear term. This just means that fi has to equal x minus alpha j. There is no other way out. Okay, this x minus alpha j is not divisible by any other irreducible. So this means that m alpha of x, which is the product of f1, f2, fs, is therefore the product of terms of the form x minus alpha j. It's a product of sum of the x minus alpha j's, sum of the terms x minus alpha j. Okay, may not be all of them, only s of them are involved, say. So it's a product of sum of these x minus alpha j's, but then that's exactly what we care about. This means in particular that m alpha of x splits in kx into a product of distinct linear factors, right? Because to begin with, all these terms here are all distinct, right? The alpha i's, remember, they're distinct to begin with. So it splits in kx into a product of distinct linear factors, and that's exactly what we needed to prove. Okay, so that completes the proof here. I mean, this is really 2 implies 3, right? So that's what we set out to prove. So we wanted to show that each m alpha of x splits as a product of distinct linear factors. Okay, so that's somewhat interesting argument again. So we start with what looks a priori like a strange assumption, or at least a weaker assumption, that the automorphism group f automorphisms of k has f as its fixed field. Okay, and that's actually enough to show that the extension is both normal and separable. Okay, it's a rather remarkable statement. Okay, and let's just quickly end with this remark about finite Galois extensions. Okay, so far everything we have said works in general, could be infinite as well, but here's a little theorem, rather important theorem that we'll prove. So let k over f be a finite extension, Observe, finite extension automatically means algebraic. Then here is yet another characterization. Then k over f is a Galois extension if and only if the following holds, if and only if the cardinality of the automorphism group is the same as the degree of the extension. Okay, so this is yet another criterion for when an extension is Galois, and again it's a completely new sort of criterion, if you wish, in terms of the degree of the extension. So it says that the extension degree should be exactly equal to the number of automorphisms that are available, that are there. Okay, and so to prove this requires some more ideas, and so we'll take a short detour through the notions of linear independence of characters and theorem of Emil Artin and so on, and then come back and prove this statement.